Ladies and gentlemen, it has been a while, but we are looking at another video. It is a post-lab from Unit 9. This deals with that relationship between F, and specifically FEL, that is the electrostatic force, and the distance between them. And in class, we created this really nice graph. And let me actually draw in the first graph that you should have saw. You should have saw F versus R look like an inverse function, and actually, interesting enough, when you play around with it and you linearize it, you figure out the relationship, or a straight line relationship, is between FEL, the electrostatic force, and 1 over r squared. In class, we noticed that the slope was Q1 times Q2, which then gave us what we have here is the equation FEL is equal to K Q1 Q2 all over r squared, and that is where this video is really going to focus your attention on. Couple of things to note about the equation. Number one, you will see this constant K hang out in front. All that is Coulomb's constant. That is 9 times 10 to the 9th, and the units with that is Newton meter squared per Coulomb squared. This is actually a constant that has to deal with free space. And in this entire class, you will see that constant will not change depending on if you are in a different form, like a vacuum versus another type of air. You might see that constant change, but for our purposes, you will never see that happen in class. The other thing to note is there is Q1 and Q2. That is the amount of charge there. And that is measured in coulombs. So notice this little Cion over here. That is the coulombs. That is how we measure charge. And just to kind of give you an idea of how charge plays along, one excess charge. So if something has a 1 extra proton or 1 extra electron, its charge is 1.602 times 10 to the negative 19th, which means you need a lot of charges in order to get 1 coulomb of charge. We'll talk about why this is such a weird conversion. Coulomb was mainly looking at current, and that was an idea in circuits that we would look at. But the more interesting aspect to this equation, and then where we're going to focus our idea today, is this idea of 1 over r squared. FEL is proportional, meaning we had a straight line when we looked at it from 1 over r squared. What does that mean? That means is as you increase the distance, the force changes at a rate of basically x squared, but you'll notice it's an inverse relationship as well, which makes this proportion look kind of weird. But in order to show this to you, I think I'm going to just show you the laboratory equipment that we were working with, which was this program. And first things to notice about both of these, no matter what the charge value is, both of those forces are the same. This is the idea behind Newton's third, equal and opposite forces. So this is a force pair, and we know that they are equal in value but opposite in direction. The next thing to note is as I move this guy around, you'll notice that the force drops, and if I move it a very short distance when these things are pretty far away, the force changes by about 0.1, and I'm moving it about, I'd say about 0.2 meters, right? Alright, so as I get these things closer and I move it 0.2 meters, you'll notice the force value changes very rapidly. So when you're really close to it, you'll notice that you have very large force changes, and then when you get really far away, and actually let me expand this out so we can really notice the difference here. When you start to get really far away, you'll notice 0.7. I'm moving it, and it's still saying 0.7, meaning we're barely changing that force value when we get really far away. This is the 1 over r squared relationship. The idea of the inverse being when the closer you are, the larger the force value, and the further away you are, the lower the change in force value. is there. So that is an idea, and we, again, to kind of look at this more mathematically, we are going to play the what-if game. And so the what-if game is like, okay, what happens if we double the distance that we are currently sitting at? So the what-if game, the easiest way to play it is, the idea is you have two charges. We're going to call this Q1 being 1, the value of 1. We're going to call Q2 having a value of 1. And we are going to call the distance between them as being 1 meter long. So if Q1 is 1, Q2 is 1, and R is 1, we would plug it into our equation. FEL is equal to K Q1 Q2 all over R squared, which is 1 times 1 divided by 1 squared, and you'll notice that we basically come out with a value of 1. We're going to ignore the constant because the constant will always be the same. So now if we want to play the what-if game, we could say, what if we double the distance between the charges, meaning that now our charges are 2 meters apart. And I can ask, what happens to the force? So again, has the Q's changed? No. We would put a 1 there, we would put a 1 there. However, our radius now is 2. So a lot of people will say, oh, if our radius is 2, we're going to get half of the amount of force. However, you got to be really careful, because we would do, again, Q1, which is 1, times Q2, which is 1, divided by 2 squared. And our force value, as you can see, is now a 4th. And so if I ask you if I'm going to double the distance, which we did here, times 2, what happened to the amount of force? We actually took a 4th of that force. So you'll start to notice by changing R, you start to change F by a rate of 1 over R squared. And so in the homework today, you'll get some practice of how to kind of work with this. The other thing that I just want to mention that you're going to see in the homework today is we are going to start looking at now placing charges around each other and then taking a look and saying, okay, there is now this thing called FEL acting on it. And what happens if I have a series of charges like this acting on this object? How would we calculate the total net force acting on it? And you will see you will have to go back to what we're normally used to, the idea of a force diagram, and being able to use all of our stuff from forces in order to determine the net force and what direction that is. So I'll leave that for you guys to play around with tomorrow. That should be a recall of what we've learned before, though. Thanks for listening, and we can cover more of these ideas tomorrow in class.